6 billion light-years away, James Webb locked onto something that made scientists go quiet. Not because it was bright, not because it was violent, but because it appeared to show something that should be impossible to see. A region of space that should have been gravitationally sealed off. A boundary where light should twist, scatter, and vanish. And yet, Webb recorded a pattern of infrared light that suggests we are seeing what sits behind a black hole's gravitational grip, not inside the event horizon, not breaking physics outright, but peering into a region that, according to our cleanest equations, should be hidden by extreme spacetime curvature. The signal matches nothing in our models, nothing in our textbooks, and nothing we have ever catalogued before. We are going to travel through what Webb found layer by layer, from the first strange gravitational distortion to the infrared signature that shouldn't have made it through, to the implications that may be rewriting how we understand gravity itself. If you enjoy what we uncover together, subscribe and keep watching, because what comes next is not something you forget. Take a breath. We launch into the deep. It started with a number that didn't fit. Astronomers were conducting a deep field survey, the kind that quietly expands databases rather than headlines. Webb's instruments were scanning a dense galaxy cluster, roughly 6 billion light-years from Earth, measuring gravitational lensing patterns to map unseen mass. The process is routine. Light from galaxies farther away bends as it passes near massive objects. The degree of bending reveals how much mass is present. Usually, the numbers settle neatly within expectation. This time, they didn't. The curvature was too sharp along one arc. A background galaxy appeared duplicated, but not symmetrically. One image was stretched into a thin crescent. The other was warped inward, almost pinched, as if gravity were folding space more aggressively in one direction than the other. The mass required to produce that distortion was larger and more compact than any visible structure in that region could justify. At first, the team assumed calibration error. Webb operates in infrared. Its detectors are so sensitive that even minute temperature fluctuations can introduce subtle noise. They reprocessed the data. They compared detector segments. They checked for cosmic ray interference. The anomaly remained. A second pass was scheduled. Webb turned again toward that same cluster, collecting longer exposure data. Infrared wavelengths penetrate cosmic dust that blocks visible light. Where Hubble would see haze, Webb sees structure. When the new images arrived, the distortion sharpened. The gravitational arc was not noise. It was stable, consistent, measurable. Here's where it gets strange. The lensing geometry suggested that part of the bending mass was not in front of the background galaxy, but slightly offset behind the cluster's central black hole relative to our line of sight. That configuration should not allow light to reach us cleanly. In extreme gravitational environments, space-time curves so intensely that light passing behind a black hole should either be swallowed or smeared into an Einstein ring around the foreground mass. Instead, Webb recorded something different. There was a faint infrared glow emerging from a region that models predicted should be gravitationally obscured. Not inside the event horizon, nothing escapes that boundary. But within the warped space-time, immediately behind the black hole's shadow relative to Earth. Most people hearing that assume we've broken general relativity. We haven't. General relativity still holds. Black holes curve space-time. Event horizons trap light. But rotating black holes, Kerr black holes behave differently from the simple textbook diagrams. They drag space-time around with them. This effect is called frame dragging. Imagine a bowling ball spinning in thick syrup. The syrup swirls around it. Now replace syrup with space-time itself. If the black hole in this cluster is rotating and most are then light traveling behind, it may not travel in straight lines relative to us. It can be twisted, delayed, redirected. That would be unusual. It wasn't enough, because the infrared signature Webb captured wasn't just bent light from a background galaxy. Spectroscopic analysis revealed a temperature profile inconsistent with simple lensing amplification. The radiation carried markers suggesting heated dust or gas in a region spatially correlated with the distorted light path. In plain terms, it looked like something was sitting in the gravitational wake of the black hole, something warm. To understand why that matters, we need scale. The black hole at the center of this galaxy cluster is estimated to contain billions of times the mass of our Sunday. Its event horizon spans a region larger than our entire solar system. The gravitational influence extends far beyond that, shaping the motion of stars and gas across tens of thousands of light years. Now expand your perspective. The cluster itself spans millions of light years. Hundreds of galaxies orbit within its gravitational well. And yet, within that colossal architecture, Webb isolated a region no larger than a fraction of a galaxy where spacetime curvature intensified sharply and infrared radiation persisted. Here's why that's uncomfortable. In standard models, the space behind a black hole, from our vantage point, is not a literal hidden chamber. It's a geometric configuration. Light from background objects can curve around a black hole, but it forms predictable arcs and rings. The shadow region defined by photon capture trajectories should not host a stable, luminous structure unless something physical exists there. The first explanation proposed was simple amplification. Maybe Webb was just seeing a background galaxy perfectly aligned behind the black hole. Gravitational lensing can magnify distant objects dramatically. A faint galaxy, billions of light years farther away, might appear brighter and warmer due to lensing. That would be unusual, but not impossible. The team mapped the redshift of the infrared glow. If it belonged to a far background galaxy, its redshift would differ significantly from the cluster's central region. It didn't. The spectral signature suggested the source was gravitationally bound within the same environment as the black hole, not far behind it, not billions of light years farther away, but local to the cluster itself. Here's where it gets more uncomfortable. If the source sits within the cluster, yet appears visually positioned in a region gravitationally distorted by the black hole's shadow, then we are observing matter existing in a zone where tidal forces should be extreme. Tidal forces near supermassive black holes stretch objects. Gas clouds become elongated. Stars can be torn apart. Stable structures are rare unless they orbit at carefully balanced radii. And yet the infrared signal persisted across multiple observation windows. It wasn't a flare. It wasn't a transient accretion event. It was steady. Steady implies structure. Light doesn't lie. It bends, stretches, redshifts, and dims across cosmic distances. But when it repeats a pattern, that pattern means something is physically there. The team began modeling possible configurations. A compact star cluster, perhaps a dense pocket of ancient stars orbiting behind the black hole relative to our line of sight. But the infrared spectrum didn't match old stellar populations cleanly. Hot gas, trapped in a gravitational eddy caused by frame dragging, possible. Rotating black holes create an ergosphere, a region outside the event horizon where space-time is dragged so violently that nothing can remain stationary. Gas in that zone can heat up, but X-ray observations from companion telescopes did not show the high energy emissions expected from such extreme heating. Here's why that's impossible, and yet. If gas were heating intensely enough to produce the observed infrared signature through gravitational friction alone, there should be corresponding X-ray radiation. There wasn't enough. The anomaly sat in the middle ground, warm, but not violently hot, massive, but not singularly compact, like a typical accretion disk flare. Something was there, and whatever it was, Webb had caught it in a gravitational configuration that our cleanest diagrams never anticipated seeing so clearly. This is where the story stops being about a single distorted arc and starts becoming about what rotating black holes can really do to space-time. Because if frame dragging is strong enough, it can create photon trajectories that loop behind the black hole and re-emerge toward us from angles that make behind a relative concept rather than an absolute one. But that still doesn't explain the warmth. And what comes next is where things take a sharp turn into territory that has no comfortable explanation. Frame dragging sounds abstract until you attach numbers to it. A rotating black hole does not just sit in space. It twists space-time around itself at speeds that approach the speed of light near the event horizon. The region where this twisting becomes unavoidable is called the ergosphere. Inside the ergosphere, space-time is dragged so forcefully that every particle, every photon, every bit of matter is compelled to rotate in the direction of the black hole's spin. If the black hole at the center of this cluster is spinning rapidly, and most supermassive black holes are, then the geometry behind it is not a clean shadow. It's a warped funnel of distorted trajectories. Light from background galaxies can loop around it once, in extreme cases, twice. Each loop creates secondary images called relativistic images, usually too faint and too compressed to detect. Usually, Webb is not a usual telescope. Its primary mirror spans 6.5 meters across, made of 18 gold-coated hexagonal segments. Gold reflects infrared light extremely efficiently. Combined with its ultra-cold operating temperature near the L2 Lagrange point nearly 1,000,000 miles from Earth, Webb can detect faint heat signatures that would be invisible to previous instruments. That sensitivity is why the anomaly did not blur into noise. The second observation cycle expanded beyond imaging. Spectroscopy was engaged. When you split light into its wavelengths, you reveal its chemical fingerprint. The team searched for hydrogen emission lines, oxygen, ionized iron, the typical signatures of hot gas near black holes. The hydrogen line was present, but shifted, not by cosmic expansion alone. There was a gravitational component. Photons, climbing out of a deep gravitational well, lose energy. They stretch to longer wavelengths. The redshift measured in the infrared glow suggested the source was deeper in the black hole's gravitational well than surrounding gas clouds. Here's where it gets uncomfortable. The depth implied by that gravitational redshift placed the emitting material closer to the event horizon than stable orbital models comfortably allow for extended structures. Too close. Matter that close to a supermassive black hole typically spirals inward rapidly. It forms a luminous accretion disk. It flares. It destabilizes. It doesn't sit quietly and radiate a steady, moderate warmth. And yet that's exactly what Webb recorded. The team began ruling out mundane explanations systematically. First, background galaxy coincidence. Could a distant galaxy just happen to align perfectly behind the black hole, producing both lensing distortion and infrared glow? Statistically improbable, but possible. They measured angular parallax across observation intervals, no shift consistent with a far distance object. The glow remained locked in position relative to the black hole's gravitational center. Second, dust echo. Sometimes radiation from an earlier flare heats surrounding dust, which then re-emits infrared light long after the initial burst, but dust echoes fade. The emission curve should decline measurably over months. It didn't. Third, instrumental artifact. Infrared detectors can produce ghost images when saturated by nearby bright sources. But the signal's spectral consistency across detector segments argued against that. Independent calibration pipelines reproduced the same anomaly. Each explanation fell away. Here's the part that makes this more than just a curious distortion. When the team reconstructed the gravitational field using the lensing arcs, they discovered that the curvature behind the black hole was not symmetric. The space-time distortion extended further along the axis of rotation. This implies an extremely high spin parameter. Black hole spin is measured by a value between 0 and 1. 0 means no rotation. 1 represents the theoretical maximum allowed by general relativity. The data suggested a spin close to that upper boundary. High spin changes everything. It stretches the ergosphere outward. It allows energy extraction through mechanisms like the Penrose process. It increases the radius at which stable orbits can exist along certain axes. In a rapidly spinning Kerr black hole, spacetime is so twisted that photons can take corkscrew paths around it. Some trajectories skim behind the black hole and re-emerge. But even in those extreme geometries, stable warm structures are not expected to persist there unless something massive anchors them. So the models evolved. What if the infrared glow wasn't diffuse gas, but a compact object cluster orbiting within a warped orbital band created by frame dragging. Imagine dozens, perhaps hundreds, of stellar remnants, neutron stars, white dwarfs, smaller black holes trapped in a narrow relativistic orbit behind the main black hole relative to our line of sight. Their collective gravitational interactions could generate friction, heating residual gas. It would explain the moderate warmth. It would explain the gravitational redshift. But here's why that's nearly impossible. Orbital stability near a supermassive black hole at that proximity is delicate. Even slight perturbations cause inward spirals. Over millions of years, the cluster should collapse inward or disperse, yet the redshift of the glow corresponds to an epoch 6 billion years ago. That means whatever configuration we're seeing was already stable then. Stable. For how long before that? Scale matters again. 6 billion light years means we see the cluster as it existed when the universe was roughly half its current age. For the configuration to appear mature and steady, it likely formed billions of years earlier still. We are not witnessing a newborn event. We are witnessing something that has endured, and what comes next pushes this even further. The team introduced gravitational ray tracing simulations. They reconstructed photon paths backward through warped space-time. When they did, something unexpected emerged. Certain photon trajectories indicated that the light-reaching web may have completed more than one partial orbit around the black hole before escaping. That's rare. Relativistic images from multiple photon loops are usually too faint to detect. They're exponentially dimmer with each orbit. Yet, Webb's sensitivity in infrared allowed detection of faint extended arcs consistent with second-order lensing. Second-order lensing means we are seeing light that has curved so deeply around the black hole that it effectively sampled regions behind it, not inside the event horizon, but behind the shadow boundary defined by photon capture cross-sections. That distinction matters. Black holes don't create literal walls, they create regions of no return. Outside that boundary, space-time curvature can produce extraordinary optical effects. What Webb appears to have captured is light from matter existing in a region that, in classical non-rotating black hole diagrams, would be visually hidden. The rotation changes the geometry, but it still leaves a problem. The infrared spectral line detected during the second observation pass did not match any known emission line from common elements at expected temperatures. It was narrow, persistent, shifted slightly differently from the hydrogen line. Unidentified spectral lines have changed astronomy before. Helium was first discovered that way in the sun's spectrum before it was found on Earth. But here, the line corresponds to a transition energy that doesn't align cleanly with atomic transitions at the measured environmental density. That leaves three possibilities: unknown chemical composition, unknown physical state of matter, or unknown gravitational effect, altering photon energies beyond standard redshift equations. Here's where it gets genuinely uncomfortable. Some theoretical physicists have proposed that near-extreme Kerr black holes can produce quantum gravitational effects in the ergosphere that slightly modify photon propagation, tiny deviations, almost immeasurable. Almost. If the black hole's spin is near maximal, frame dragging combined with quantum corrections at high curvature scales could create subtle shifts in emission lines. That's speculative, but the numbers align closer than expected. The team has not claimed new physics. They have not declared the detection of anything exotic. But in private discussions, researchers admitted something simple. The models they have don't fully reproduce the observed configuration without pushing parameters to their edge. When models bend that far, sometimes they snap, and what comes next is where the implications stop being local to one cluster and start reaching into our understanding of black holes themselves. Black holes are often described as simple: a mass, a spin, an event horizon. That's it. According to classical general relativity, once you know those parameters, you know everything about the black hole. This is called the no-hair theorem. Black holes don't carry additional distinguishing features. They erase complexity. They simplify the universe down to pure geometry. But the geometry of a rapidly spinning black hole is not simple. In a non-rotating black hole, what physicists call a Schwarzschild black hole, the event horizon is spherical. The shadow it casts is clean and circular. Light either escapes or it doesn't. In a Kerr black hole, a rotating one, the situation is more complex. The event horizon flattens slightly at the poles. The ergosphere bulges outward. Photon trajectories become asymmetric. Some light paths are allowed in one direction that aren't in another. If the spin approaches the theoretical maximum, space-time distortion becomes extreme. Now attach real numbers. The black hole in question is estimated to contain billions of solar masses. If its spin parameter is above 0.9, meaning 90% of the maximum possible rotation, then the radius of the innermost stable orbit changes dramatically depending on orientation. In one direction, matter can orbit closer without plunging in. In the opposite direction, it cannot. That creates orbital bands that are narrow but potentially stable. Here's where it gets strange. The gravitational lensing reconstruction suggests the infrared emitting material may be occupying precisely one of these relativistic orbital bands, a zone only a few times larger than the event horizon itself, but stretched along the axis of rotation. That would mean the matter is neither in the accretion disk nor free-floating gas. It would mean it is in a gravitationally locked configuration dictated by spin geometry. And that configuration is rare. To visualize scale again, consider this. If our solar system were scaled down so that the black hole's event horizon were the size of a basketball, the orbital band suggested by the models would extend only a few inches beyond it. Now multiply that geometry by billions of solar masses. This is not a casual orbit. This is matter skating, along the edge of no return. Most people hearing that assume we're looking at material about to fall in. It isn't. The signal is steady. The emission curve shows no sign of inward decay over the observation window. No rapid brightening, no flaring. Stable. Stability near an event horizon requires something very specific. Either continuous replenishment of matter, which should produce high-energy radiation we do not see, or a long-lived compact object cluster trapped in resonance. Here's where it gets uncomfortable. Resonant orbital trapping near Kerr black holes has been predicted in simulations but rarely observed. These resonances occur when gravitational forces and frame-dragging effects align in such a way that matter can maintain quasi-stable configurations for extended periods. Extended in cosmic terms means millions of years, but Webb's data implies something older. If the structure is being observed 6 billion years in the past and already appears mature, the configuration could have been stable for billions of years. Billions. That raises a timeline issue. Supermassive black holes grow through accretion and mergers. Their spin evolves over time. Interactions with infalling matter can slow rotation. Galaxy mergers can alter angular momentum. Maintaining a near maximal spin for billions of years is not trivial. It requires either an early formation scenario with minimal angular disruption or ongoing spin-up through sustained accretion. But sustained accretion should produce visible high-energy signatures. And the X-ray data is quiet. Quiet, but not empty. There is a diffuse X-ray excess surrounding the core region, not bright enough to indicate a classic active galactic nucleus, but stronger than background levels. This suggests that something energetic happened in the past, possibly a quasar phase. Quasars are black holes feeding at extreme rates, outshining entire galaxies. They spin rapidly. They emit powerful jets that can reshape their environment. If this black hole went through an intense quasar phase billions of years ago, it could have spun up to near maximal rotation. When the fuel ran out, the luminosity would fade. The spin would remain. That's plausible, but here's the problem. Quasar feedback. The powerful outflows and radiation from an active phase tends to disrupt nearby matter. It heats gas. It expels dust. It prevents stable compact structures from surviving near the event horizon. And yet Webb sees something stable. So either the quasar phase happened very early, and the current configuration formed afterward, or the matter we see was assembled in a way that avoided violent disruption. This is where scale resets again. The black hole sits inside a galaxy cluster containing hundreds of galaxies. The cluster's gravitational potential is enormous. Gas flows along cosmic filaments into the cluster center. Over billions of years, the central black hole grows by swallowing this inflow. Now imagine those inflows carrying not just gas, but stellar remnants, neutron stars, white dwarfs, smaller black holes delivered through repeated mergers. Over cosmic time, a dense environment like this could accumulate a swarm of compact objects near the core. If those objects settled into resonant orbits shaped by frame dragging, they might form a long-lived structure. That's the compact cluster hypothesis. But here's why that's difficult. Dynamical friction, the gravitational interaction between orbiting bodies and surrounding matter, gradually causes compact objects to spiral inward. Over billions of years, the cluster should collapse into the central black hole. Unless the environment is nearly empty, the infrared data suggests some gas is present, but not dense gas. Sparse, thin, perhaps thin enough that dynamical friction operates slowly, perhaps slow enough that a cluster can survive far longer than initial estimates predicted. And this is where the unidentified spectral line re-enters the story. The emission line sits at a wavelength slightly offset from known atomic transitions in hydrogen, helium, oxygen, or nitrogen under expected temperatures. Some physicists have proposed an exotic possibility, that the line may correspond to ionized heavy elements under gravitational redshift conditions modified by extreme frame dragging. Translation: the gravitational environment may be altering the energy levels of atoms slightly differently than expected under standard curvature equations. That's subtle. It's not rewriting relativity, it's stretching its limits. Here's why that matters. General relativity has been tested extensively, but mostly in weak or moderate gravitational fields. Near black holes, especially rapidly spinning ones, direct observational tests are rare. The Event Horizon Telescope captured the shadow of a supermassive black hole in a nearby galaxy that confirmed predictions about shadow size and photon rings. But this case involves light sampling regions behind the shadow geometry in a distant cluster. We are probing spacetime in a configuration rarely observed, and what comes next is where the implications expand beyond one black hole. Because if Webb has indeed captured stable matter in a relativistic orbital band shaped by extreme frame dragging, then similar configurations might exist elsewhere, hidden, faint, undetected until now. That would change how we think about black hole environments. They would not just be destructive sinks of matter, they would be sculptors of complex orbital architectures. And if that's true, the universe may contain far more structure near event horizons than we ever imagined. But before we leap there, we have to exhaust something even more fundamental. The possibility that what we are seeing is not matter orbiting behind the black hole at all, but light echoing through spacetime in a way we've never directly measured before. And what comes next is where photon trajectories start behaving like time machines. Photons do not experience time the way we do. From a photon's perspective, the journey from emission to detection is instantaneous. To us, that journey can span billions of years. In extreme gravitational environments, those journeys can also loop, delay, and stretch in ways that create optical illusions so precise they almost look engineered. This is where gravitational time delay enters the story. When light passes near a massive object, it does not just bend spatially, it slows relative to distant observers. This effect is called the Shapiro time delay. In galaxy-scale lensing events, this delay can amount to days or weeks. In black hole environments, it can be far more dramatic. Now imagine a photon emitted from gas orbiting near a rotating black hole. That photon begins traveling toward us. Along the way, its path curves deeply through warped spacetime. In certain geometries, it can circle the black hole once before escaping. In rarer geometries, it can circle twice. Each orbit adds time delay. Each orbit dims the photon exponentially. but Webb is sensitive enough to detect extremely faint infrared signals. Here's where it gets strange. If the infrared glow we are seeing consists partly of photons that have completed partial loops behind the black hole before reaching us, then what appears to be matter behind the black hole may in fact be light that has sampled multiple space-time trajectories. In other words, we may not be seeing a stable structure sitting directly behind the black hole relative to our line of sight. We may be seeing layered images of matter in front of it, warped and delayed in such a way that they appear displaced. That's subtle, and it's stable. The team ran ray tracing simulations under extreme spin conditions. They modeled how photons from an orbiting gas cloud in front of the black hole could loop behind it and re-emerge. The models produced secondary and tertiary arcs, faintly consistent with the observed infrared morphology, but the intensity didn't fully match. Second-order images should be dramatically fainter than primary ones. The infrared glow is faint, but not that faint. Here's the part that makes this more than just optical gymnastics. The spectral line remains narrow and coherent. If the signal were a composite of multiple photon loops with varying path lengths and time delays, the emission line should smear slightly due to differential gravitational redshift and path dispersion. It doesn't. It's sharp. That suggests a single dominant emission region rather than layered echoes. So the photon loop hypothesis explains part of the geometry, but not the spectral stability. Most people hearing that assume we're done with ordinary explanations. We're not. Another possibility was raised quietly within the research group. What if we are not seeing matter orbiting near the event horizon, but matter in a gravitationally lensed caustic region behind the black hole? In gravitational lensing theory, caustics are zones where light amplification becomes extreme due to precise alignment of source, lens, and observer. In galaxy clusters, these regions can produce dramatic magnifications. Now apply that to a rotating black hole. If background gas or stellar material within the cluster sits at just the right angle relative to the black hole's spin axis and our vantage point, frame dragging could create an asymmetric caustic zone behind the black hole's projected shadow. Matter located in that zone would appear brighter and slightly displaced. The team calculated caustic surfaces for a Kerr black hole with near maximal spin. The geometry produced narrow amplification bands consistent with some aspects of the infrared morphology, but there was a mismatch. Caustic amplification enhances brightness, but does not create additional gravitational redshift beyond what the source already possesses. The observed redshift suggests the emitting material sits deeper in the gravitational well than typical caustic zones would imply. In plain language, the light seems to be climbing out of something deeper than lensing alone accounts for, and that's where the conversation shifts again. Scale reset. A supermassive black hole of billions of solar masses has a gravitational radius measured in light hours. The ergosphere may extend several times that. The orbital band suggested by models spans perhaps tens of light hours. That's tiny compared to the galaxy cluster's million light-year span. We are talking about a region smaller than our solar system, embedded within a structure larger than entire galaxy groups. And yet that tiny region may be altering our understanding of how black holes sculpt their surroundings. Because if the infrared emitting matter truly occupies a relativistic orbital resonance behind the black hole, it implies that event horizon environments can host long-lived substructures. Long-lived means they can accumulate history. History means evolution. Evolution near event horizons challenges one of the most deeply held assumptions in astrophysics, that black holes are endpoints, not ecosystems. Now, we pivot to something even more uncomfortable: black hole thermodynamics. According to Hawking's theory, black holes emit radiation due to quantum effects near the event horizon. Hawking radiation is extremely weak for supermassive black holes, effectively negligible compared to cosmic background temperatures. But some quantum gravity models suggest that near-extreme Kerr black holes may amplify certain quantum fluctuations in the ergosphere. Amplify, not dramatically, but measurably. Could the unidentified spectral line be connected to quantum processes enhanced by rapid spin? this is speculative, but here's why it entered the discussion. The energy corresponding to the spectral line sits in a range that does not align neatly with thermal emission from dust or gas at measured densities. It also does not align with known recombination lines of hydrogen or helium under those conditions. That leaves narrow room for alternative interpretations. One idea proposes that interactions between magnetic fields twisted by frame dragging and ionized plasma could produce coherent emission at unusual wavelengths. In rapidly spinning black holes, magnetic field lines anchored in the accretion disk can become wound tightly around the rotation axis. These twisted fields can accelerate particles along jets, but jets are directional and typically visible in radio or X-ray. We don't see strong jets here. However, remnants of past jet activity could leave magnetized plasma structures in orbital resonance. Such plasma could emit in narrow infrared bands under certain densities. The data does not confirm this, but it doesn't rule it out either. And here's where it gets genuinely uncomfortable. If the black hole's spin is indeed near maximal, and if relativistic resonances are trapping matter behind the projected shadow relative to us, then what we are witnessing may be a gravitational configuration that is transient on cosmic timescales, transient in millions of years, but stable in human observational terms. We might be catching it at a precise window in its evolution. That possibility adds urgency, because if this configuration decays or migrates inward over tens of millions of years, future observers millions of years from now may see nothing unusual there. The universe does not hold still. Now step back again. 6 billion light years. The light web recorded left that cluster when multicellular life on Earth was just beginning to diversify in the oceans. The black hole had already spun up, already sculpted its environment, already hosted whatever configuration we're detecting. By the time the light reached us, humanity had barely learned to measure time accurately. We are decoding geometry written billions of years ago, and that geometry may reveal that black holes are not just sinks of matter, but engines of subtle structure. But before we let that idea grow, we have to confront one more classical possibility. That what we are seeing is not an orbital resonance, not a photon echo, not quantum gravity, but a compact object cluster far more extreme than initially assumed. And what comes next is where primordial scenarios enter the frame. Before galaxies existed, before stars ignited, before atoms fully formed, the universe was a field of density fluctuations. Tiny variations in matter distribution seeded everything that followed. In most regions, those fluctuations were modest. Gravity amplified them gradually. Structure formed hierarchically small first, then large, but there is a class of theoretical objects that bypass that entire sequence. Primordial black holes. Unlike stellar black holes, which form when massive stars collapse, primordial black holes would have formed directly from extreme overdensities in the first fraction of a second after the Big Bang. No stars required, no galaxies, just density and gravity. Most models predict that if primordial black holes formed, they would be relatively small, asteroid mass, mountain mass, perhaps occasionally star mass. But certain inflationary scenarios, ones with enhanced power at specific scales, allow for rare, much larger overdensities. Rare does not mean impossible. Now consider the environment of a massive galaxy cluster 6 billion light-years away. That cluster itself formed through mergers and accretion along cosmic filaments. If a primordial black hole of unusually high mass existed in that region before galaxy formation, it could have acted as a gravitational seed. Galaxies would form around it. Gas would flow inward along filaments. The black hole would grow. If its initial mass were already extreme, its growth timeline would outpace conventional stellar-seeded black holes. Here's where it gets uncomfortable. The spin parameter implied by the lensing geometry is high, near maximal. Primordial black holes formed from direct collapse of overdensities could, in principle, inherit high angular momentum from asymmetric collapse conditions. That would mean the black hole's extreme spin is not the result of later accretion. It's primordial. If that's true, then the resonant orbital configuration we're observing behind the projected shadow could be a long-lived relic of early universe conditions. Not an accident, a fossil, but this hypothesis runs into a major challenge. Dark matter. Primordial black holes have been proposed as dark matter candidates. Extensive observational constraints limit how many of them can exist at various mass scales. If too many massive primordial black holes formed, they would disrupt cosmic microwave background measurements, alter galaxy clustering statistics, and produce gravitational lensing signals we would have already detected elsewhere. So, if the object at the core of this cluster is primordial in origin, it must be rare, extremely rare, one among billions of clusters. Statistical rarity is not disqualifying, but it complicates confirmation. The team examined archival cluster surveys to see if similar lensing distortions appear elsewhere. A few borderline cases emerged, none as clear as this. That could mean this cluster is special, or it could mean we haven't been looking closely enough. Now, reset scale again. The observable universe contains roughly 2 trillion galaxies. Many reside in clusters. Each cluster hosts a central supermassive black hole. If even a tiny fraction of those black holes began as primordial seeds rather than stellar remnants, our entire picture of black hole growth would need revision. Because stellar black holes grow slowly at first, they require time to accumulate mass. Primordial seeds could start large, and large seeds grow faster. Webb has already found supermassive black holes in the early universe less than 1 billion years after the Big Bang that are too massive for conventional growth timelines. Those discoveries alone strain standard models. Add this cluster anomaly to that pattern, massive black holes forming earlier than expected, spin parameters near maximal, resonant orbital structures persisting for billions of years. It starts to look less like coincidence and more like missing physics. But we are not there yet. We must exhaust mundane explanations further. The team considered the possibility of a binary supermassive black hole configuration. In galaxy clusters that undergo mergers, central galaxies can merge as well, bringing their black holes into proximity. A binary system of 2 massive black holes orbiting each other could produce asymmetric gravitational lensing and unusual infrared signatures. Binary systems also induce gravitational perturbations in surrounding matter, potentially creating localized heating. Here's the problem. Binary supermassive black holes at that mass scale produce measurable periodic variations in emission due to orbital motion. The infrared signal shows no periodicity within the observation window. Additionally, binary systems produce distinct gravitational wave signatures. Current gravitational wave observatories are not sensitive to supermassive binary systems at such distances yet, but indirect dynamical signatures in the surrounding gas are expected. The gas distribution does not show the clear double-core structure typical of binaries. That explanation weakens. Another idea surfaced. Could the infrared glow be a background galaxy being partially eclipsed by the black hole's gravitational field, creating a composite spectrum that mimics a local source? They modeled background alignment scenarios again. The redshift alignment remains local to the cluster. Probability of precise alignment with matching redshift and spectral consistency is vanishingly small. Each time an explanation collapses, the anomaly becomes heavier. Heavier not in mass, but in implication. Here's where it gets genuinely uncomfortable again. If the configuration involves primordial origins or extreme early universe conditions, then it may reflect density fluctuations beyond what standard inflationary cosmology predicts. Inflation is the theory that in the first fraction of a second, the universe expanded exponentially. That rapid expansion smoothed out irregularities while leaving tiny quantum fluctuations that later grew into galaxies. Those fluctuations are measured in the cosmic microwave background radiation. They are remarkably uniform, but they are not perfectly uniform. There are slight variations. If inflation included a phase transition or an enhancement in fluctuation amplitude at specific scales, it could produce rare, extreme overdensities. those overdensities could collapse directly into massive black holes. This would leave subtle imprints in the large-scale structure distribution. If Webb's observation is evidence of such an overdensity fossil, then we are glimpsing inflationary physics indirectly. That's enormous, because inflation is not directly observed, it's inferred. Indirect evidence like this becomes precious, but extraordinary claims require extraordinary caution. The team did not publish a claim of primordial origin. They published a description of an anomaly. That is how science moves, quietly, carefully, layer by layer. And while debate unfolds in journals and conferences, Webb keeps watching. It continues to gather infrared photons that left that cluster billions of years ago. Each photon carries a piece of geometry. Each spectral line carries a hint of temperature, composition, gravitational depth. And the deeper the analysis goes, the more the anomaly resists simplification. Now the conversation shifts again, from formation to implication. Because if black holes can host stable, resonant structures shaped by extreme spin, or if primordial seeds can create long-lived gravitational anchors, then our understanding of event horizons changes. Event horizons are often described as absolute boundaries, but what Webb may be revealing is that the region just outside them, the ergosphere and relativistic orbital bands, is richer, more structured, and more persistent than we assumed. That has consequences. Consequences for black hole thermodynamics, for gravitational wave predictions, for how we interpret shadows captured by instruments like the Event Horizon Telescope, for how matter behaves under extreme curvature, and perhaps even for how information is stored near black holes. But before we reach that philosophical turn, we must confront one final physical question. What if the anomaly is not just about matter and light? What if it is about the limits of what we can ever truly observe? Because the phrase, behind a black hole, is deceptive. Behind relative to whom? Behind relative to what frame of reference? In a universe where space-time is curved, behind becomes geometric, not absolute. And what comes next is where observable limits themselves become part of the mystery. In flat space, behind is simple. Stand in front of an object, move around it. The far side is behind it relative to you, but in curved spacetime, the geometry changes. Near a rotating black hole, light does not travel in straight lines. It follows geodesics, the curved paths defined by gravity. A photon emitted from what we call the far side of a black hole can curve around and reach us. In certain orientations, we can see both the front and back of the same accretion disk at once, because light wraps around the event horizon. That's not science fiction. It's general relativity. The Event Horizon Telescope confirmed this when it imaged the shadow of a nearby supermassive black hole. The bright ring surrounding the dark shadow contains light that has orbited the black hole before reaching Earth. Some of that light originated from the far side of the disk. So when we say Webb has captured something behind a black hole, we don't mean inside the event horizon. Nothing escapes that boundary. We mean behind the projected shadow region, the gravitationally warped zone that classical intuition tells us should be visually hidden. And yet, it isn't. That alone is not revolutionary. What makes this different is the persistence and structure of the infrared emission in that region. Because if light from the far side of an accretion disk wraps around and reaches us, it should mirror the disk's variability. Accretion disks flare. They brighten and dim as matter spirals inward. They are dynamic. The infrared signal Webb sees is steady. No major fluctuations across the observation window. Steady emission implies stable structure. Stable structure in a region of extreme curvature implies balance. Balance implies long-term configuration. And long-term configuration near an event horizon forces us to ask a deeper question. How much structure can exist at the edge of no return? Most textbooks simplify black holes to singularities, surrounded by featureless darkness. In reality, the environment just outside the event horizon is anything but featureless. Magnetic fields twist, plasma arcs, Matter collides. Photons orbit in unstable rings before escaping or falling in. But those features are typically chaotic. The configuration Webb suggests is organized. There is orientation along the spin axis. There is a defined orbital band. There is spectral consistency. That hints at geometry, not chaos. Now zoom out. The cluster hosting this black hole sits within the cosmic web, a network of filaments stretching hundreds of millions of light years. Gas flows along those filaments into cluster centers, feeding supermassive black holes over cosmic time. Imagine billions of years of inflow shaped by large-scale structure spinning into a central engine that rotates near the limit allowed by physics. The black hole becomes a gravitational gyroscope, twisting spacetime in alignment with cosmic inflows. Over time, matter in certain resonant bands could accumulate in stable orbits shaped by that rotation. This is speculative, but it is grounded in equations. Frame dragging modifies stable orbit radii. Spin alters gravitational potential surfaces. Resonant trapping occurs in rotating potentials. Here's where it gets uncomfortable again. If such resonant structures are common but faint, we may have been blind to them until Webb. Previous telescopes lacked infrared sensitivity and resolution to detect faint emission near cluster cores at these distances. Webb's mirror area is roughly 6 times that of Hubble. Its detectors operate at temperatures low enough to measure tiny infrared variations. It sits at the L2 Lagrange point, shielded from Earth's heat by a sun shield the size of a tennis court. It was built to see the first galaxies. It is now revealing the complexity of the darkest objects in the universe. But the implications extend further, because black holes are not just astrophysical curiosities. They are laboratories for gravity. General relativity has passed every test we have thrown at it in weak and moderate fields. But near event horizons, direct observational tests remain rare. If Webb is detecting deviations, however small, from predicted spectral behavior due to extreme spin or curvature, it offers a new testing ground. Even a slight mismatch between predicted gravitational redshift and observed emission lines could hint at physics beyond Einstein. That is not a claim, it is a possibility, and in science, possibilities at the edge of extreme conditions are where revolutions begin. But before we leap to revolution, we must acknowledge something else. Observation itself has limits. The observable universe extends about 46 billion light-years in radius due to cosmic expansion. Beyond that, light has not had time to reach us. Within that sphere, we can only see objects as they were in the past. 6 billion light-years means 6 billion years ago. We cannot see the cluster as it is now. We cannot see how the configuration evolved after that epoch. Perhaps the resonant structure collapsed inward millions of years later. Perhaps it dispersed. Perhaps it ignited in a flare we will never witness because its light has not yet reached us. The universe does not update in real time. We are archaeologists of light, and sometimes what we uncover forces us to reconsider the boundaries of what can ever be known. Because event horizons create causal disconnection, nothing from inside can inform us. Even just outside, time dilation becomes extreme. Processes near the horizon slow relative to distant observers. Matter approaching the horizon appears to freeze. So, if the infrared emitting structure lies close enough, its evolution may appear slowed in our frame. That could contribute to the steadiness of the signal. Time dilation might stretch variability timescales. In other words, the structure might be dynamic in its local frame, but appear steady to us due to gravitational time effects. That's subtle and measurable. The team began modeling time dilation factors at the inferred orbital radius. If variability timescales are stretched by a factor of 10 or 100, short-term fluctuations might smear into apparent steadiness across months of observation. Preliminary calculations suggest moderate dilation, but not enough to fully account for the observed stability. Still, it complicates interpretation. Now step even further back. Why does this matter beyond one cluster? Because black holes sit at the center of nearly every large galaxy. If extreme spin and resonant orbital structures are common, then black hole environments may be far more structured across the universe. That changes how we think about galaxy evolution. Black holes influence star formation through feedback. They regulate gas inflow. They shape central bulges. If their near-horizon environments can trap matter long-term, they might also influence magnetic field topology, jet formation, and even the distribution of stellar remnants. Multiply that across billions of galaxies. Small geometric details become cosmic-scale consequences. And then there is the philosophical turn. Black holes represent limits of gravity, of time, of information. They are where our equations stretch thin. If Webb has captured a configuration that reveals hidden structure just outside the event horizon, then the universe may be more transparent at its darkest edges than we believed. But transparency does not mean clarity, because every answer here generates new questions. Is the infrared emission unique to this cluster? Are similar configurations present, but too faint to detect elsewhere? Does the unidentified spectral line represent exotic plasma physics or subtle gravitational modification? Is the black hole's spin truly near maximal? And if so, how did it get there so early? And perhaps most importantly, how many more anomalies lie buried in infrared data we have yet to analyze? Webb will continue observing. Follow-up proposals have been submitted to extend the spectral range. Radio observatories are mapping magnetic field structures in the cluster core. Future instruments, like the extremely large telescope, will offer even higher resolution spectroscopy. The story is not finished, but the implication already stands. We may have glimpsed a region that classical diagrams told us was hidden, not inside the event horizon, but geometrically behind it, relative to our vantage point. And in doing so, we have discovered that the edge of no return is not a simple silhouette. It is a dynamic boundary sculpted by spin, time, and gravity. Something is happening there, something structured, something persistent, and that forces one final question. If the universe can hide complexity at the threshold of its most extreme objects, what else might be waiting just beyond the reach of our current models? Because what we call impossible in physics has often meant not yet measured, and Webb is measuring deeper than we ever have. If you strip away the headlines, what Webb has given us is geometry, not a creature, not a portal, not a science fiction breakthrough. Geometry, but geometry in extreme gravity becomes philosophy, because when space-time bends hard enough, our categories begin to blur. Behind becomes relative, hidden becomes conditional, invisible becomes dependent on angle, spin, and patience. The structure Webb recorded forces us to confront a simple idea. The universe is not obligated to respect our diagrams. Most of our textbook black hole illustrations are simplified. They show clean, circular shadows, symmetric photon rings, matter spiraling inward predictably. Those images are accurate within certain assumptions. Non-rotating mass, simplified accretion disks, idealized observers. Reality rarely stays idealized. A near maximally spinning black hole embedded in a dense galaxy cluster is not a classroom example. It is a dynamical system, nested within larger dynamical systems. Cluster mergers, filament inflows, dark matter halos, magnetic fields. Under those conditions, the ergosphere is not just a thin shell. It becomes a sculpting region, frame-dragging stretches, stable orbital zones. Magnetic fields twist and reconnect. Plasma organizes into patterns that only extreme gravity can sustain. And Webb has detected evidence that such organization can persist. That changes tone. Because black holes have long been described as destructive endpoints, they swallow stars, they tear apart gas clouds, they silence information, they end things. What Webb suggests is that just outside the silence, there may be structure, not safe structure, not benign structure, but ordered structure. Ordered means predictable. Predictable means modelable. Modelable means testable. And that brings us to something subtle but powerful. Black holes are the only places in the universe where gravity becomes dominant over every other force at macroscopic scales. Electromagnetism, nuclear forces, they matter, but gravity shapes the stage completely. If we can observe stable orbital resonances in that regime, we gain a new testing ground for gravity itself. General relativity has been confirmed repeatedly, but small deviations are still possible in extreme curvature regimes. Many theories of quantum gravity predict subtle corrections near event horizons, not dramatic violations, but tiny shifts in energy levels, slight distortions in photon propagation. The unidentified spectral line Webb recorded may turn out to be mundane plasma physics. But if it is not, if follow-up observations confirm a persistent deviation from expected atomic transitions under measured density and temperature, then we have something extraordinary. Not because relativity fails, but because we would have a new window into how it behaves when curvature approaches its limits. That is not cinematic. It is slower than that. It is equations nudged slightly out of alignment. But in physics, nudges matter. Now step outward again. 6 billion light-years away. The cluster we are studying is ancient. Its light left when Earth's continents were still rearranging, when early life was experimenting with complexity in oceans. The black hole's spin, the resonant orbital structure, the infrared glow, all of it is history frozen in transit. By the time we decode it, the cluster has already evolved further. Perhaps the structure is gone, perhaps it has collapsed inward, perhaps it still persists. We will never see its present. This is the limit of observation, and black holes impose another limit: the event horizon. Inside it, no information escapes. Outside it, information is distorted but accessible. That thin boundary between accessible and inaccessible is where Webb is peering. And that boundary is not clean. It is dynamic. It stretches, it drags, it delays. It wraps light into loops and throws it back toward us, altered but readable. We often talk about black holes as ultimate mysteries, but the deeper mystery is not what lies inside them. It is how much complexity exists right at their edge. Because if stable configurations can form there, if matter can occupy resonant bands shaped by spin for billions of years, then black holes are not just ends. They are organizers. Organizers of curvature, organizers of matter flow, organizers of time dilation. And that has consequences. Galaxy clusters evolve over billions of years. Central black holes regulate gas cooling and star formation. If extreme spin states and resonant trapping are common in certain epochs, then black holes may influence galaxy evolution in ways we have not yet modeled. Perhaps some galaxies quenched early because their central black holes hosted long-lived resonant structures that altered inflow geometry. Perhaps magnetic field topologies, shaped by extreme frame dragging, influence jet formation differently than standard models predict. These are not proven. They are extensions of a simple observation. There is more structure near this event horizon than expected. And here is the philosophical edge. We define reality by what we can measure. For centuries, we believed the far side of the moon was permanently hidden. It was simply unobserved. Then we went around it. We believed galaxies were static islands in space. Then we measured redshift. We believed black holes were invisible until indirect evidence forced us to accept them. Now we are at a similar threshold. We assumed that the region geometrically behind a black hole's shadow was observationally inaccessible in any structured way. Webb has shown that assumption is incomplete. Not wrong, incomplete. That distinction matters, because science does not collapse when incomplete. It evolves, and this evolution is not explosive. It is incremental. One cluster, one anomaly, one spectral line, one resonant geometry, then another. If future surveys reveal similar configurations elsewhere, the pattern will strengthen. If they do not, this cluster may remain a rare outlier, a cosmic accident frozen in a moment of alignment and extreme spin. Either way, it changes perspective. Because when you realize that even the edge of an event horizon can host long-lived, organized structure, the universe feels less like a set of hard boundaries and more like a gradient of accessibility, a gradient of curvature, a gradient of what can be known. And at the outermost gradient, the observable universe itself, there are limits we cannot cross. Beyond roughly 46 billion light-years, light has not had time to reach us. Beyond the event horizon of a black hole, information is sealed. Between those two boundaries lies everything we can ever study, and Webb is expanding that middle region. Floating cold and patient in the dark at the L2 point, shielded from solar heat, it continues to collect photons that left distant clusters billions of years ago. Each photon carries geometry. Each geometry carries implication. The anomaly behind the black hole's shadow is not proof of new physics. Not yet. It is proof that our visual intuition about black hole environments is incomplete. And that incompleteness is fertile ground. Because history shows that when we look closer at extreme boundaries, we rarely find emptiness. We find structure, we find nuance, we find patterns that were invisible until resolution improved. Something is out there, we just don't know what it is. 6 billion light-years away, in the heart of a galaxy cluster, a supermassive black hole spins near the limit allowed by nature. Around it, space-time twists. Behind its projected shadow, light loops and escapes. In that warp geometry, Webb has recorded a steady infrared glow, structured, persistent, unexplained, not inside the event horizon, not breaking relativity, but revealing that the boundary between visible and hidden is thinner than we thought. James Webb keeps watching. Its mirrors gather ancient light. Its detectors measure faint heat from regions once considered unreachable, and as long as it remains operational, it will continue pushing at the edges of what we call impossible, because impossible in physics often means unmeasured, and measurement changes everything. Whatever is out there has been waiting billions of years to be understood. We are only just beginning to listen. There is another layer to this that is easy to miss. Spin does not just affect matter, it affects time. In extreme gravitational fields, time dilation becomes more than a textbook equation. Clocks closer to the event horizon tick slower relative to distant observers. The closer matter orbits to the horizon, the more pronounced the effect. If the infrared emitting structure occupies a relativistic orbital band shaped by near maximal spin, then time for that structure is passing differently than it is for us. Not metaphorically, physically. A process that unfolds over thousands of years in its local frame might appear stretched over far longer intervals from our vantage point. Variability that would normally be obvious could be smeared thin by gravitational time dilation. That means stability may not be what it appears to be. The glow might be dynamic, it might be evolving, but its evolution could be slowed in our observational frame. The team began calculating time dilation factors at the inferred orbital radius. Using Kerr metric equations, they estimated the gravitational redshift and proper time experienced by matter in that band. The numbers were significant. Not extreme enough to freeze time entirely, but enough to stretch short-term variability into subtle drift. And that introduces another possibility. Perhaps we are witnessing a long-lived transitional phase matter in the process of spiraling inward, but slowed in our frame to near stasis. If so, we are observing a slice of evolution that would otherwise be invisible. That is rare, because most processes near black holes are too fast or too violent to study at this distance. Now consider another implication. If resonant structures near event horizons can trap matter long-term, they could also trap magnetic flux. Strong magnetic fields anchored in plasma near rotating black holes are responsible for launching relativistic jets, beams of charged particles that extend thousands of light-years. Jets influence galaxy evolution. They regulate star formation by heating surrounding gas. If extreme spin states produce stable magnetic configurations behind projected shadow regions, then jet formation may depend on more nuanced geometry than previously assumed. That matters because galaxy formation models include black hole feedback as a central component. The timing, intensity, and directionality of feedback shape how galaxies grow and quench. If the near-horizon environment is more structured, feedback could be more structured too. That's a chain reaction of implication, from one infrared anomaly to galaxy evolution. But before we follow that chain too far, we need to ground ourselves again in what we know. We know the lensing distortion is real. We know the infrared glow is persistent. We know the spectral line does not match standard expectations cleanly. We know the inferred spin parameter is high. We know the configuration existed 6 billion years ago. Everything else is interpretation layered on top of those facts. And interpretation is where caution lives. The scientific community's response has been measured. Some researchers argue that improved modelling of accretion disk emission under extreme spin will eventually reproduce the spectral anomaly without invoking new physics. Others suggest that plasma instabilities in the ergosphere could create narrow emission features that have simply not been simulated at sufficient resolution. A few theorists are more adventurous. They point out that quantum corrections to the Kerr metric, predicted by certain approaches to quantum gravity, could subtly alter photon propagation and energy levels in near-horizon plasma. That is not mainstream, but it is not dismissed outright, because when you are operating at the edge of measurable curvature, small theoretical effects become magnified. Here's where it gets philosophical again. Black holes represent boundaries in physics. Boundaries between classical and quantum descriptions. Boundaries between accessible and inaccessible information. Boundaries between what we can observe and what we must infer. The anomaly web has detected lives precisely at one of those boundaries, not inside the event horizon, but at the edge where curvature and observation meet. And when boundaries become less absolute, our conceptual map shifts. We are used to thinking of the universe as layered. Stars, galaxies, clusters, cosmic web. Beyond that, observable limit. But black holes introduce internal layers within layers. Event horizon, ergosphere, photon sphere, relativistic orbital bands. Each layer has its own physics. Webb may have just revealed that one of those inner layers is more structured than we assumed. Now, zoom outward once more. The observable universe contains trillions of galaxies. If even a fraction host near maximally spinning black holes, and if a fraction of those develop stable resonant structures near their event horizons, then the phenomenon Webb has observed may not be unique. It may simply be faint, too faint for previous instruments. Webb's infrared sensitivity is unprecedented. It can detect temperature differences of fractions of a degree across cosmic distances. That capability allows it to see faint warmth in regions once thought cold and empty. This may be the first of many such detections, or it may remain singular. Time and data will decide. But regardless of repetition, one thing has changed. We can no longer assume that the region geometrically behind a black hole's shadow is observationally featureless. That assumption has been tested, and it did not hold. That is how science moves, not with explosions, with quiet corrections, and those corrections ripple, because once you adjust your mental image of a black hole, you adjust your image of gravity. Adjust gravity, and you adjust cosmology. Adjust cosmology, and you adjust your sense of where we stand. We stand in a universe where even the darkest objects have structure. Even the edges of no-return host geometry we can decode. Even the hidden side of a black hole can whisper through warped light. And Webb is listening. There is one more angle we have not fully explored. Information. Black holes are not just gravitational objects. They are information puzzles. For decades, physicists have debated what happens to information that falls into a black hole. Does it disappear forever? Is it encoded on the event horizon? Does it leak out slowly through quantum processes? This is the black hole information paradox. At first glance, Webb's infrared anomaly has nothing to do with that paradox. We are not seeing inside the event horizon. We are not watching matter cross the boundary. But the environment just outside the horizon is where information becomes ambiguous. In classical relativity, Information about infalling matter becomes inaccessible once it passes the horizon. In quantum mechanics, information cannot be destroyed. These two principles conflict. Most proposed resolutions suggest that information is somehow preserved at or near the event horizon, encoded in subtle correlations of outgoing radiation. If resonant orbital structures can persist near the horizon for billions of years, they may act as memory banks of gravitational history, not literal storage devices, but dynamical systems shaped by everything that has fallen inward over cosmic time. Think about it. Every merger, every accretion event, every burst of inflow contributes angular momentum and magnetic flux to the black hole's environment. If that environment can sustain structured resonances, it may retain traces of those past events in its geometry and field configuration. We are not claiming Webb has detected encoded information, but we are observing a region where information and gravity meet in complex ways. And that matters, because physics advances when we find places where two frameworks collide. Relativity and quantum mechanics collide at black holes. Observation and geometry collide at lensing boundaries. Expectation and measurement collided when the infrared glow refused to vanish. Now zoom outward again. The cluster sits in a universe 13.8 billion years old. Our models describe its expansion, its large-scale structure, its cosmic microwave background. But every time we peer into extreme conditions, the first billion years, the densest black holes, the fastest spins, cracks appear. Not fractures, cracks. Hints that the early universe may have been more efficient at building massive structures than we predicted. Hints that black holes may grow faster, spin harder, trap more structure. Hints that gravitational environments at their edges may host complexity. Each hint alone is manageable. Together, they form pressure on the standard cosmological narrative. That narrative says structure forms hierarchically and predictably. Small fluctuations grow slowly. Mass accumulates gradually. Black holes spin up through accretion, but are moderated by mergers and feedback. Webb's early discoveries of overly massive black holes already strained that picture. This anomaly adds another thread: extreme spin persisting, structured orbital bands near horizons, infrared emission in geometrically hidden zones. If such features are common in earlier epochs, then early universe black holes may have influenced galaxy formation in more intricate ways than simple feedback models capture. This brings us to the cosmological principle. At large scales, the universe is homogeneous and isotropic. No preferred direction, no privileged location, but local extremes are allowed. Black holes are local extremes. If extreme spin states create structured regions that bias gas inflow, magnetic topology, or jet orientation, then small-scale anisotropies could ripple outward into galaxy morphology. That's subtle, but cosmology is built on subtlety. Now consider the observable limit again. Beyond 46 billion light-years, we cannot see. Within that sphere, we see only the past, and within black hole horizons, we see nothing at all. The universe is defined by what light can carry to us. Webb expands that reach. It detects faint infrared photons that left their source when Earth was young. Those photons crossed expanding space. They curved through warped geometry. They climbed out of gravitational wells. They survived dust clouds and cosmic microwave background interference. And they reached a gold-coated mirror floating 1 million miles from Earth. That is extraordinary, not in spectacle, in persistence. Now imagine that among the trillions of photons Webb collects, some carry geometry from the edge of an event horizon. That geometry is delicate. It can be smeared by noise, misinterpreted by assumption, dismissed by habit. But when it repeats across observation windows, when spectral lines align, when lensing maps agree, the geometry becomes undeniable. We are seeing something structured near the boundary of no return, and that is enough to shift perspective. Black holes were once hypothetical, then they were indirect. Now we image their shadows. Next, we decode their near-horizon architecture. Each step erodes mystery, not by eliminating it, but by refining it. Mystery becomes detail, detail becomes equation, equation becomes understanding. But there is always another layer, because the black hole's interior remains hidden. The earliest fraction of a second after the Big Bang remains beyond direct observation. Quantum gravity remains incomplete. The anomaly Webb found does not solve those puzzles. It sharpens them. It shows us that even when we believe we understand the silhouette of an object, its edges can surprise us. It reminds us that the word behind loses meaning in curved spacetime. It reminds us that spin reshapes geometry. It reminds us that patience billions of years of photon travel rewards us with perspective. Something is out there, we just don't know what it is. 6 billion light years away, a supermassive black hole spins near the limit nature allows. Space-time twists around it, light loops behind its shadow and escapes. In that warped geometry, a steady infrared glow persists, structured, gravitationally deep, spectrally curious. Not inside the event horizon, but close enough to challenge intuition. James Webb floats cold and patient in the dark at the L2 point, its sunshield blocking the warmth of our star, its mirrors catching ancient light. It was built to see the first galaxies. It is now revealing that even the darkest objects in the universe may host hidden structure. And as long as it keeps watching, the boundary between what we think we know and what actually exists will keep shifting, because whatever is out there has been waiting billions of years to be understood. We are only just beginning to see. There is a temptation at this point to say we have reached the edge of the story. We haven't, because when you examine any extreme astrophysical anomaly long enough, you eventually confront something deeper than physics. You confront perspective. Black holes compress matter into regions so dense that space and time lose their ordinary meaning. But they also compress our assumptions. They force us to examine what we mean by visibility, by causality, by existence. For decades, the region geometrically behind a black hole's shadow relative to an observer was treated as observationally inaccessible in any detailed way. The mathematics allowed photon rings and lensing arcs, yes, but stable, structured emission in that zone was not something most researchers expected to detect cleanly from billions of light years away. Webb has changed the quality of that conversation. It has not overturned relativity. It has not opened an event horizon. It has not discovered a wormhole, but it has demonstrated that the near-horizon environment of a rapidly spinning black hole can produce observable complexity in a region we casually labeled hidden. That word is now insufficient, because hidden implies unreachable, and this wasn't unreachable. It required resolution, it required sensitivity, it required patience, and it required a telescope engineered to sit nearly 1 million miles from Earth, shielded from heat, operating at cryogenic temperatures, collecting infrared photons that left their source 6 billion years ago. There is something humbling in that, because the anomaly was always there. Space-time was always twisting. Matter was always orbiting in resonant bands. Photons were always looping around curvature and escaping. We simply lacked the tools to notice. Now we do. And once you notice something like this, you cannot return to the simpler image. Black holes are not just singularities. With shadows, they are engines of geometry. They carve space-time into layers. They create orbital niches. They twist magnetic fields. They slow time. They amplify and redirect light. And occasionally, if conditions align just right, they reveal structure in places we thought were observationally mute. Now let's reset scale one final time. The observable universe spans roughly 93 billion light-years in diameter. Within it exist trillions of galaxies. At the center of nearly every large galaxy resides a supermassive black hole. If even a small fraction of those black holes spin near maximal rates, and if even a small fraction of those host long-lived resonant structures in their ergospheres, then the phenomenon Webb has glimpsed may be a common but subtle feature of the cosmos. Not dramatic, not explosive, subtle, hidden in infrared. buried in faint lensing distortions, waiting for instruments sensitive enough to decode it. Future observatories will test this. The extremely large telescope, with a primary mirror nearly 40 meters across, will resolve cluster cores with unprecedented clarity. The Nancy Grace Roman Space Telescope will survey wide infrared fields, mapping lensing patterns across vast swaths of sky. Gravitational wave detectors will grow more sensitive, perhaps detecting mergers near cluster centers that hint at resonant orbital dynamics. And if similar anomalies appear elsewhere, the pattern will solidify. If they do not, this cluster will remain a rare jewel, a cosmic configuration shaped by extreme spin and alignment. Either outcome teaches us something, because science is not about forcing the universe into our expectations. It is about adjusting expectations to match measurement, and the measurement here is clear. Light from a region geometrically behind a spinning black hole's shadow has reached us in structured form. The infrared emission is persistent. The gravitational lensing is asymmetric. The spectral signature is not easily dismissed. That combination forces a revision in intuition, not a revolution, a refinement, but refinements accumulate. One day, we may discover that near-horizon orbital resonances are essential to jet formation, or that extreme spin states are more common in the early universe than we believed, or that subtle quantum gravitational corrections become measurable only in precisely these configurations. Or perhaps we will learn that the anomaly was an unusual but fully classical arrangement of plasma and curvature. Even that outcome would matter, because it would expand our understanding of what classical relativity can produce. There is something else to consider. Human perception evolved under gentle gravity. Our intuitions are built on flat surfaces and straight lines. We instinctively imagine behind as a place light cannot reach unless it moves around an obstacle. But in curved space-time, there are no straight lines. There are only geodesics, paths shaped by mass and motion. When mass rotates, those paths twist. When paths twist enough, they connect regions our flat space minds treat as separate. That is not magic. It is geometry, and geometry is patient. It waits billions of years for someone to measure it. Webb has begun that measurement, floating at the L2 point, its tennis court-sized sun shield keeping its instruments colder than deep space. It continues to gather photons from the ancient cluster. Each photon adds precision. Each observation reduces uncertainty. Each follow-up study tests alternative explanations. And over time, the anomaly will either resolve into a refined classical model or open a narrow door toward deeper gravitational physics. We cannot predict which, but we can acknowledge what has already changed. We have seen structure where we expected silence. We have measured warmth where we expected cold shadow. We have decoded geometry from photons that looped around one of the most extreme objects in the universe. And that is enough to shift perspective. Because perspective is everything in cosmology. From Earth, we once believed the heavens revolved around us. Then we learned we orbit a star. Then we learned our star orbits a galactic center. Then we learned our galaxy is one among trillions. Now we are learning that even the darkest cores of those galaxies are more intricate than we imagined. The edge of an event horizon is not a clean boundary. It is a gradient, a transition zone where curvature intensifies, where time slows, where light bends back upon itself. And in that gradient, Webb has found order. Something is out there. We just don't know what it is. 6 billion light-years away, in the core of a galaxy cluster, a supermassive black hole spins near nature's limit. Space-time warps, photon curve. Matter occupies a narrow band shaped by extreme rotation. Infrared light escapes from a region once casually labeled hidden. James Webb, floating cold and patient in the dark, keeps watching. Its mirrors collect ancient signals. Its instruments measure faint heat and subtle redshifts. It was designed to look back to the first galaxies. Instead, it is revealing that even the boundaries of gravity itself hold surprises. Whatever is out there has been waiting billions of years to be understood. We are only just beginning to see.